Okay, so we were discussing about limit of a function uh, when limit is infinite. So what we discussed last time, limit of a function at a point. So when we say limit x tends to a, fx is equal to infinity. What is the definition of limit x tends to a f of x is equal to infinity? Can you see my screen? Yes.
Voice is low.
Okay, can you see my screen?
Yes, sir.
Yes.
Yes, sir.
Okay, so there was connection problem, and now you can see the screen, no problem. So please confirm.
Yes, sir, it's visible.
Okay. So uh, what is the limit extends to f of x as equal to infinity? What does it mean? So limit x tends to a, f of x is infinity, means given m, there exists delta. So limit at a, limit of function at a is infinity. That means given m, there exists delta such that whenever distance of x from a is less than delta, then f of x is greater than m. So this is what we discussed last time. So okay, so from this, prove that limit x tends to 0 from right side, f of x is infinity. So how to prove this? If you look at the graph of this function, this is graph of uh, okay, f of x is equal to where f of x is 1 by x. So this is my function. So f of x is equal to 1 by x. How is the graph? And if you go closer and closer to 0, then function is approaching towards infinity. So uh, okay, how will you prove that limit x tends to infinity, f of x is equal to infinity? So given m. So what is delta? So that the definition is satisfied, means given any m, can you find delta when you are sufficiently close to 0 or x is in delta neighborhood of 0, then f of x is greater than m. So see this figure. If you are given any larger number m, if you are given any larger number m, can you produce delta so that if you are in this range, so 0 plus delta, then f of x is greater than m, right? So what we want, delta, such that whenever distance of x from 0 is less than delta, then f of x is greater than m. Fine. So here we want right hand limit, not left hand limit. So for right hand limit, that is what we expect if x is in 0 to 0 plus delta, then f of x is greater than m. So such delta we want. Now can you tell me what could be delta? What should be delta? Yes. Yes. So we want f of x. F of x means 1 by x is greater than m. Such x we want to find, or such delta we want to find. So 1 by x greater than x, m means what? X is greater than, x is less than what?
1 by m.
1 by m. So uh, that means x is less than 1 by m. See the figure or graph again. I want, suppose I choose larger number m, then I want delta, so that if I choose x in this delta neighborhood, f of x is greater than m, right? And so obviously, what is the choice for delta? When f of x is greater than m, if x is less than 1 by m. So can you tell me what should be the choice for delta?
1 by m.
So choose delta is equal to 1 upon m plus 1. I will choose sufficiently smaller delta. That is better, right? Then if uh, distance of x or x is in 0 to 0 plus delta, means x is in 0 to delta, I am choosing delta is equal to 1 upon m plus 1. So if x is in between 0 to delta, then 0 less than x less than delta. But delta is 1 upon m plus 1. That means x is less than 1 upon m plus 1. Then what is f of x? F of x is 1 by x, right? So when I choose x less than delta, that means x is less than 1 upon m plus 1. Therefore 1 upon x is greater than m plus 1 and m plus 1 is greater than m. So can I say that 1 by x is greater than m? Yes. Do you agree?
Yes, sir.
Fine. So therefore given any m, I can give you delta. Whenever x lies in between 0 and delta, f of x is greater than m. So thus for any m greater than 0, we can produce delta such that whenever 0 less than x less than delta, that means x lies in between 0 and delta, then f of x is greater than m. Therefore, what we can conclude, if you approach to 0 from right side, 1 upon x approaches towards infinity. Fine. Now, prove that limit x tends to 0, e raised to 1 by x is infinity. Right, so how will you prove this? Limit x tends to 0 from right side, 1 by x tends to infinity. Yes. Is it possible to prove this? What we want to prove, given m, there exists delta such that whenever 0 less than x less than delta, then for such x, f of x is greater than m. So is it possible to do this? Yes.
Yes, sir.
So how will you do this? So given m, right? Now want delta. So try to do these calculations naturally. So we want delta, but basically what is f of x? E raised to 1 by x, right? And we want to make this greater than m. We want this greater than m. If so, when f of x is greater than m, if e raised to 1 by x is greater than m, that means e raised to 1 by x greater than m. That is if. But when e raised to 1 by x greater than m, if I take log of both sides, 1 by x into log e greater than log m, which is equivalent to, how is it possible? If I apply log on both sides, it remains greater. How is it possible?
So because log is increasing function.
Very good. So log x is increasing function. So therefore this is true. So, but log is 1. So 1 by x is greater than log m, right? Which is possible if x is less than 1 upon log m. Now can you tell me delta? Can you?
So 1 by log m.
Right. So choose delta is equal to sufficiently smaller, no harm. Choose 1 upon log m plus 1. Still smaller delta you can choose. Right. Still smaller than this. So if you choose delta is equal to 1 upon log m plus 1, so certainly this quantity is positive because we are choosing m sufficiently larger, so log m is positive. So that therefore if 0 less than x less than delta, delta is 1 upon log m plus 1, then verify that f of x or e raised to 1 by x is greater than m. What is the conclusion? Limit x tends to 0, limit x tends to 0 e raised to 1 by x, if you approach from right side, is infinity. Okay, any doubt in this? Is it clear what I am saying?
Yes, sir.
Right. Now you also think about what is limit x tends to 0 from left side 1 by x. What is this limit? If you look at the graph of 1 by x, what is this limit as x tends to 0
minus
from
infinity.
minus infinity? Now how will you prove this? Given what? Given m, there exists delta such that. So this is left hand limit. So minor delta less than x less than 0. That means there is a delta neighborhood, half neighborhood of 0 because we are approaching from left side only. Implies what about f of x? F of x is less than minus m. Given any positive m, we can produce delta such that whenever x is in this, so minor delta to 0. If whenever x is in this range, f of x is in less than minus m. I have chosen sufficiently larger positive. So in this range, f of x is less than minus m. So, and this is easy to see, right? Correct?
Yes, sir.
Now, and therefore, second point, what is limit x tends to 0 from left side e raised to we are approaching from left side. And so what is this limit? What do we expect? What could be this limit? 1 by x approaches minus infinity, right? So limit x tends to 0 from left side, 1 by x approaches minus infinity. So e raised to what is it?
0.
0. Correct. Do you see this? Because 1 by x approaches infinity and therefore e raised to 1 by x approaches e raised to minus infinity or e raised to infinity, which approaches to 0. Approaches means what? Not exactly equal to, so it approaches. So this is what we can understand. Now, can you see the nature of this function e raised to 1 by x? There are other things you can think about. So what is another thing? What is limit x tends to, we just thought about limit as x tends to x tends to 0. Now what is the limit x tends to infinity e raised to 1 by x? You should think about it. What is limit x tends to minus infinity e raised to 1 by x? You also still think about this, and can you sketch the graph of this function? Right? Can you sketch the graph of this function? So can you sketch the graph of f of x is equal to e raised to 1 by x? So what is the nature of function near 0? So if you approach from left side, it is tending towards infinity. That is what we saw. If you approach from right side, it tends towards 0. That is what we saw. And I am giving you hint. The nature of graph is like this for this function, not horizontal, but like this. That means what happens if x tends to infinity, what happens if x tends to minus infinity, and accordingly you can understand the nature. So limit x tends to infinity of this is 1. You think about this. Limit x tends to minus infinity is also 1, and therefore if you approach x approaches infinity, then nature of function is like this, it approaches towards 1. If x approaches minus infinity, then also f of x approaches 1, and therefore nature of function is like this. Then question I would like to ask is, does limit x tends to 0 e raised to 1 by x exist? What can you say about limit at 0? What is right hand limit and what is left hand limit at 0?
So both are different.
Different, right? Of course no, because limit x tends to 0 from right side e raised to 1 by x is infinity, and limit x tends to 0 from left side is 0. Therefore, limit x tends to 0 e raised to 1 by x does not exist. So, we'll discuss this uh, different type of exponential functions during practical session. Right. So, prove that limit x tends to 1 x square plus 2 upon x minus 1 is infinity. So similarly you think about this. Also recall what we discussed yesterday. The limit x tends to infinity f of x is L. So how will you make this definition of limit x tends to infinity f of x is equal to L? So what could be the definition? Just apply the definition of limit. But now here x tends to infinity. So uh, given epsilon, there exists alpha such that if x greater than alpha, then distance between f of x and L is less than epsilon. Do you agree with this definition? Do you understand? It is compatible with our basic definition of limit. Yes?
Yes, sir.
Yes, sir.
Right. So please ask if you have any doubt. Because x approaches infinity. X approaches infinity means what is the neighborhood of infinity? So x greater than alpha. Everything greater than alpha, you can say that neighborhood of infinity. And limit is L. So as x approaches towards infinity, limit is some number L, means f of x is in epsilon neighborhood of L. That's it. And third point, you should understand limit x tends to infinity, f of x is infinity. So how to understand this? How will you make the definition if you understand previous two definitions? Yes. How would you understand this?
Given m greater than 0, there exists alpha greater than 0 such that if x is greater than alpha, then f of x is greater than m.
Very good. So given any larger number m, because function is going towards infinity, whatever larger number you give, I will give you some larger number alpha such that x greater than alpha implies f of x is greater than m. Fine. So therefore, prove that limit x tends to infinity, x is infinity. Interesting to prove this. Secondly, prove that limit x tends to infinity, x square is infinity. Right. Prove that limit x tends to infinity, e to the power x is infinity. So there are any other some other functions also for which you would come across this situation. So for example, if you want to prove that limit x tends to infinity, x is infinity. So how will you prove this? So how to, what is the claim? Given m, there exists alpha such that x greater than alpha implies f of x greater than m. This is what our aim. So given m, start with m, want alpha. But what is f of x in this case? F of x is x. So what is the choice for alpha? What we
m.
want f of x is greater than m, but f of x is x, x greater than m. So from this we understand that we choose alpha is same as m, right? Then x greater than alpha, that means f of x is same as x, which is greater than alpha, which is m. So in this way, for every m, we can produce alpha. And ultimately, what it suggests is, if you look at the f of x is equal to x function, whatever m you give me, I can give you alpha. If your x is greater than alpha, then f of x is greater than m. This is what it's mean. So in this way, you can think about what is the limit at infinity and infinite limit, or limit at infinity is infinity. So this idea should be known to you, right? Because at several occasions we come across such kind of limits. Fine. So what is the purpose to study all these things, limit and all this business, right? So let us start with a simple example. So let f of x is equal to x square if x is not equal to 1, and 0 if x is equal to 1. So my first question is sketch the graph of f. What is the graph of this function? So do you see the graph? I have chosen very simple function. So f of x is equal to x square, right? So 1 is here up to 1, and at 1 there is a break, and after 1 again it is x square. Do you understand? It is a graph of f of x is equal to x square. Yes?
Yes, sir.
Fine.
Yes, sir.
Okay. Now, uh, first of all, let me not define it at 1. I am not defining this function at 1. Yes. So this is a graph. Fine. At 1 function is not defined. Now, the question is, can you draw the graph? the graph of f without lifting pen. Is it possible? Without lifting pen, can you draw
No,
this?
sir.
No.
No, sir.
Fine. Okay. Now next question I would like to ask. Does what is limit extends to 1 fx? Does the limit exist?
Yes, sir.
Yes. Because if you look at limit extends to 1 right hand side, and what is limit extends to 1 from left hand side? Both are equal, so limit exists and limit is 1. Fine. Okay, so we cannot draw, so therefore limit x tends to 1, f of x is 1 exist, but the graph of f is not a continuous curve. Yes, do you agree? Graph of f is not a continuous curve. Yes.
Yes, sir.
Yes. Yes, sir.
So why there is a problem? The function is not defined at 1, correct? Yes.
Yes, sir.
Next, suppose I define the function f of x is equal to x square if x is not equal to 1 and 0 if x is equal to 1. Now it is defined at 1 also. Then what is limit x tends to 1, f of x is 1, that's fine. And if you sketch the graph again for same function at 1, again there is a hole at 1, and at 1 value of function is 0, or suppose value of function at 1 is 10, no problem. So what is the value of function at 1? 10. That means again graph of function is not continuous curve, right? So graph of f is not a continuous curve. Fine. So why this happened? Given function is defined at 1, f of 1 is 10 is defined, right? F of 1 is 10, this value is defined. Still graph is not a continuous curve. Now you tell me when this graph will be a continuous curve, when we can draw the graph without lifting the pencil.
When limit of f of x at x is equal to 1 is equal to f of 1.
Right. So now if we define a function f of x is equal to x square if x is not equal to 1 and 1 if x is equal to 1, that is f of x is equal to x square for every x. Then what happens? Limit x tends to 1, f of x is 1 and value of function at 1 is also 1. Secondly, see the graph. So at 1 value is same as f of 1. Graph of f is a continuous curve. Continuous means what? We can draw the graph without lifting the pen or pencil. That is the idea, right? So such function is said to be continuous at 1. Now we say that this function is continuous at 1. Right, now I want to make a definition of continuous function. I want to make a definition of continuous function. Now you tell me what should be the definition of continuous function.
For all a belonging to the domain, the limit of x tends to a f of x should be equal to f of a.
Okay, let a subset of R, A belongs to A now. Now I am saying necessarily note this, A is a member of A. When we define the limit, we did not bother about whether A is in the domain or not, right? Here, when we talk about limit at A, continuity at A or limit at A, we should, okay, I will leave the space here. Suppose f is a function defined on A to R, then we say that f is continuous at A if, from the previous discussion, the function was continuous at A when this happened, if limit at 1 is same as value of function at A. So when this happened, what I should say in the definition now, how to make the definition? Yes, f is continuous at A if please complete the sentence.
Limit of x tends to a f of x is equal to f of a.
Okay, if limit x tends to A fx exists, first of all this limit should exist. Second, that limit at A should be equal to value of function at A. This is what we mean to say the function is continuous at A. That is why what we observed from the previous example. But here when we talk about limit at A, what is the guarantee that, or when we can talk about limit at a point? What is the restriction? What is the condition that we should put on in the definition?
X should be in the delta neighborhood of A.
No. When I say that function is continuous at A, means limit at A exists and it is equal to value of function at A. Whenever as soon as I am using the word limit, what condition on A we should put? Just recall what we discussed when we talk about limit.
A is a cluster point of A.
Very good. So A is a cluster point of A. Then only we can talk about limit, because we already seen the examples that if I look at set 1, 2, 3, 1 is in the, and if you define a function on this set A, still limit does not exist at 1. Even function is defined at 1, 2, 3, limit does not exist. Do you understand this? Yes? Do you understand what I am saying?
Yes, sir.
Yes.
So, A must be a cluster point of A, and then when we say that, okay, I am saying that this is a definition 1. Why 1? That will come to know later on. But anyway, so as x, if x is, A is a point of A and A is a cluster point of A, suppose f is a function defined on A, so of course f of A exists. Why? Why f of a exists? Because we are assuming that A is in the domain A point A is in the set A, and function is defined everywhere on set A. So function is defined at A. So f of A exists, no problem. Function is defined at A because we are choosing A from the domain. While talking about limit, we didn't put this condition ki A is in the domain. Function might not be defined. Okay, this definition is clear. Am I right?
Yes, sir.
Okay. So that is that is what does it mean? F is said to be continuous at A if limit x tends to A, f of x is equal to f of A. That means in terms of definition of limit, what I should say here, limit f is continuous at A means this last expression. If what?
Limit x tends to a, f of x is equal to f of a.
Means what? Given epsilon, there exists delta such that given epsilon, see, limit of something is some number, means what? Limit of something is some number means what? Given epsilon, there exists delta such that, what is next line?
X belonging to delta neighborhood of a, then f mod of f of x minus f of a is less than epsilon.
Right. So, what does it mean? The distance of x from a is less than delta, then distance of f of x from f of a. Now limit is f of a, value of function at a. Here necessarily limit is value of function at a. So this is less than epsilon. But here I won't write it is greater than 0. Why I won't write this?
Because a is included in the domain.
Function is defined at a, and therefore distance of x from a is less than delta, then distance of f of x from f of a is less than epsilon. So here x is equal to a, then f of a makes sense because a is in the domain and function is defined at a, no problem at all. Note this difference, right? Note this difference, this red circle greater than 0, this is not there in case of continuity, right? So that is minor delta less than x minus a is less than delta implies f of x minus f of a is less than epsilon, or x belongs to a minor delta to a plus delta, provided x is in domain, then f of x is in f of a minus epsilon to f of a plus epsilon, or x belongs to v delta a, then f of x is in epsilon neighborhood of f of a. This is what we observe from this. This is what we observe from this. But here we are coming from limit. We are coming from the limit. But again, this definition is not a complete. This definition is not complete. Why? We'll see this. Let a is equal to 1, 2, 3, and f is a function defined on this set a to r. Suppose f of x is equal to some function x square. Right. Now questions. I have questions. So does limit x tends to 1 fx exist? What is your answer?
No, sir.
No. And we have discussed this, right? All of you know the reason. A very basic and interesting question. Is f continuous at 1? It's a very interesting question. Is f continuous at 1?
No, sir.
Okay, so my set domain is 1, 2, 3. So these are 3 points in the domain, and value of function is 1, 4 at 2 and 9 at 3. So this is the graph, you can say, right? And is f continuous? Anybody else? What is the answer? Anybody else? Is f continuous at 1? So I think somebody, Aditi, said no, but answer is yes. And why? This is a very interesting thing. Limit does not exist, and therefore we want to make the concept of continuity very, very general, more general, right? So next time we'll see this, why it is continuous at 1. Or you think about it. If you have better answer, we can discuss, right? So now we'll stop here. Next time we'll see this, which is very interesting to see why this function is continuous. Yes, any doubt?
Excuse me, sir.
Yes.
Sir, I wanted to know something related to the real number system. Sir, if we take A to be empty set, then sir, what's the supremum and infimum of that?
Did you attend our initial lectures?
Yes, sir, I did.
So if A is equal to empty set, right, then 10 is an upper bound of A, of empty set. Do you agree?
Yes, sir.
Okay. So some number is not upper bound means what? It is a negation of definition of upper bound. 100 is also upper bound,
Yes, sir.
or minus 5000 is also upper bound.
Yes, sir.
And then what is every real number is upper bound?
Yes, sir.
Is upper bound, and therefore what is the least upper bound?
Minus infinity.
Does not exist. Minus infinity is not in our real world.
Yes, sir. But if we take extended real number system, then
That is
we
different
would
story.
find.
Extended means you can bring out whatever outside our universe in our universe, then that is a different story. We are talking about real numbers. Extended system means we are, which is not in our real world. Do you understand this?
Yes, sir.
If you consider extended real number, that is a different story. Then you have everything.
Okay, sir. I got it.
Right.
Yes, sir.
Fine. So, okay, we'll stop here.